Right angle triangle questions. So again, the setup for all of these related rate problems is the same. We read through the question, we see which rates of change we know, we determine which rate of change we want to find, and at what moment. So two cars leave the same location at the same time. One travels east at 60 kilometers per hour, and one travels north at 45 kilometers per hour. So I'm going to think of going north as my y value, and going east as an x value. So in this case, I know that dx dt is 60 kilometers per hour, which means that x is some function of time. We know that dy dt is 45 kilometers per hour. So y is a function of time. And we're asked to find out how fast they are separating from each other. So we'll introduce another variable, and we want to find dz dt, which also means z is a function of time. And we want to find it, maybe I'll just write at, time is 2 hours. So this is our first question that has 3 variables in it. And we have to come up with some way to relate those 3, and the easiest way, since it's a right angled triangle, is you know that a squared plus b squared equals c squared. So x squared plus y squared would equal z squared. And we can use explicit differentiation and do the derivative with respect to time here. So the derivative of x squared would be 2x dx dt. The derivative of y squared would be 2y dy dt. And the derivative of z squared would be 2z dz dt. And we want to find it at 2 hours, but notice there's no place in here to plug in 2 for time. However, if we think about x being the distance going north, y being the distance going east, and z being the distance between them, at 2 hours, since we're going 45 kilometers per hour north, does it make sense that that would be 90 kilometers to the north? And 60 kilometers per hour to the east. This will be 120. Anybody know any mental math tricks for doing a squared plus b squared equals c squared on this one? Without doing 90 squared plus 120 squared equals 40,000 and then square rooting that and getting 200? No? So, often in questions, the 3, 4, 5 triangle is hidden. You can see this is also going to be a 3, 4, 5 triangle because it's just multiplied by 30. Oh, and I made a mistake in my mental math. I said 200, but it's 150. So if we did a squared plus b squared equals c squared, we would get 150 there. It is just this triangle times by 30. And now we can plug in all of our information. We know that the x is 120, and dx dt was 60. Y is 90, and dy dt was 45. And z is 120. And we want to solve for dz dt. Yes.
Isn't it 150?
Yes, it's 150. That would have ruined everything. So take out our calculator and do the following. and you'd get 75 kilometers per hour. Now, what's intriguing or interesting, if we look at just the speeds, this one was 45 kilometers per hour, this one was 60 kilometers per hour. Can you see that this is also a form of the 3, 4, 5 triangle? If I divide this by 15, I get 3. This by 15, I get 3. So if I take 5 and multiply it by 15, I would get 75 kilometers per hour. And the question says, am I allowed to do that, though? Am I allowed to just square the speeds and make it work? Is there some way that I could prove that that's still, like, you might just say, well, I think it makes sense because it's a right angle triangle, and now we're just dealing with a different unit. What's also possible, which I think is kind of neat, is if you take this equation, and first of all, if we divide everything by 2, you would just get x dx dt, right, plus y dy dt equals z dz dt. And the x distance, x is a distance, right? And distance is speed times time. Okay? What is the speed of x? Well, that's x's rate of change times time. And can you see that I could do that with y? Since it's speed, y's speed is dy dt times time, and same thing with z. And if I substitute those into this equation, I would now get, instead of x, t times dx dt squared plus t times dy dt squared equals t times dz dt squared. Then you can divide everything by t. You do show that dx dt squared also plus dy dt squared equals dz dt squared. So in this situation, with all 3 of them changing, we could have just done a squared plus b squared equals c squared right from the beginning with the speeds. Although, I think the expectation in a question like this would be to set up like we did, sort of our standard way of, what do we know? What are we trying to find? Can we set up an equation? And can we solve that equation? But it just so happens in this example that we would have been able to do a sort of shortcut method for this. Since the next question is basically the same, I'm going to leave this one because it would just be doing the same thing again. So you can try this on your own. But we'll look at another triangle question here. So we've got a house. Sometimes it's nice to draw a picture. Oh, nice little window in this house. Maybe a door, and someone put a ladder leaning against the house. So here's our ladder leaning against the house, but unfortunately, it is sliding down from the house and sliding away. So this is what's happening right now. The top of the ladder is coming down, the bottom of the ladder is extending out. So again, what we have here is a right angle triangle, and things that are changing is this x distance is changing, and this y distance is changing. We want to find the rate at which the ladder is moving downward, and we're told the rate that it's moving away, so we know that dx dt is 2 feet per second, which means x is some function of time. We want to find out how fast dy dt is changing. tells us that y is a function of time at 12 feet. And notice in this one, there is no dz dt because z, or the hypotenuse, is always 20. So in setting up our equation here, again, it makes another right angle triangle. But this time we can plug in a value for z because the hypotenuse is always 20. Take the derivative with respect to time. Oh, and we would have 2x dx dt plus 2y dy dt. And the derivative of 400 will just be 0 because it's a constant. Now we want to find dy dt, but we notice in the equation we also have a y value that we'd have to plug in. We know the x value. We know the x value is 12. Could we find the y value at that moment? Yes, because we could do a squared plus b squared equals c squared. And maybe notice today is brought to you by hidden 3, 4, 5 triangles. It is another 3, 4, 5 triangle. And if you see them, it makes your math a lot quicker and easier. Because this is just the 3, 4, 5 triangle times by 4. So now we can plug everything in. We know that x was 12. We know that dx dt was 2. We know that y is 16. If I move this 48 over and divide by this 32, and it makes sense that our answer is negative because that top of that ladder is coming down. So what makes right triangle questions maybe a little bit trickier is you often have to draw the triangles and do some figuring, okay? And common mistakes I've seen in questions like this is you draw the triangle and people think, oh, I should put 12 in for x because they tell me x is 12. But we have to take into consideration when things are changing. That x value is changing all the time. The y value is changing. We're allowed to plug in 20 for the hypotenuse because that is always going to be the same. It's not changing. But if things are changing, then you have to leave the variables in place before you take the derivative. Okay. Similar to right-angled triangle questions are similar triangle questions. And if I think back to when I first started related rate problems, these are the ones that I remember the most. Maybe they were the hardest for me. It's like, oh yeah, the shadow questions. What's happening? So here we have a spotlight on the ground, shines on a wall 10 meters away. A man 2 meters tall walks from the spotlight towards the wall at a speed of 1.2 meters per second. How fast is his shadow going down when he's 3 meters from the wall? So visualizing this is the first part which makes this question hard. You have to imagine a wall. So there's a wall. There is a spotlight. There we go, let's draw some. Spotlight on the ground, 10 meters. So we know that this distance is 10 meters. And there's a guy walking 2 meters, and as that spotlight hits him, there would be a shadow on the wall over there. Now we have to determine which rates of change have they given us. They tell us that the man walks from the spotlight towards the wall at a speed of 1.2 meters per second. Okay? So now this is the first tricky part to these questions, is determining where you're going to put variables and what you're going to call them, because you could put variables in different places here. I'm going to choose to make this distance from the spotlight to the man X, because we're told that he is moving away from the spotlight at 1.2 meters per second. So can you see that X is increasing, and so that 1.2 meters per second is going to be positive. Of course, it means X is a function of time. You don't have to write that. It helps us understand the implicit differentiation that we're going to be doing. And as this man walks towards the wall, your Y value is going to be decreasing. And that's what we want to find. We want to find dy dt at x equals, and this is where we have to be a little bit careful, how fast is the shadow on the wall decreasing when he is 3 meters from the wall? X won't be 3. X will be 7. Because if this is x, does it make sense that this section over here would be 10 minus x? And so we're trying to find it when x is equal to 7. So this is the choice. I chose to put the x there. There are sometimes students will put the x here. That's perfectly fine, because then x would be 3. But if I put the x at the 10 minus x spot, then dx dt would be negative 1.2, because it would be getting smaller. And you could do the same question that way, and it would solve perfectly the same. Now, to solve these questions, you have to go back to a unit you did in grade 9, which I can say with most certainty you've completely forgotten about similar triangles, although it's not a hard thing to revisit. In fact, we have already talked about similar triangles today when we did the 3, 4, 5 triangle, and just say, oh, you double it, right? And the key thing about similar triangles, so let's just look at our 3, 4, 5, and let's look at a 6, 8, 10, doubled it. They're going to be similar. Now, some properties of similar triangles that can help you in equations, okay? The property that you remember the most from grade 9 is being able to look at this and go, oh, this is just times by 2, okay? But there are other parts to a similar triangle which are going to be important for us in solving this. And another part of a similar triangle that's important is to notice, and this is really beautiful because it connects like your early basic understanding of trigonometry and everything else, is to notice that ratios are the same. In other words, if I took 4 over 5 on this one, and I took the 8 over 10 on this one, can you see that those ratios are equal? 4/5 and 8/10. And why are they equal? Well, they're both sine theta. If they're similar triangles, this angle would be the same. So sine would be the same, cos would be the same, tan would be the same. All the ratios would be the same. But in a question like this, we're not talking about sine, cos, and tan. We're just noticing that we have this red triangle here is similar to this big purple triangle here. And even as the man moves and those triangles change shape, at any moment when you stop, those two triangles are always similar. Because this angle here is always the same in the red triangle and the purple triangle. And because they're similar triangles, we can use these ratios to create an equation. Just like 4/5 is equal to 8/10, there are different ratios. I could do the two sides, I could use the side and the hypotenuse, and I can make an equation. What do I for sure want to do? I for sure want to make an equation that involves my y, and I for sure want to make an equation that involves my x. So when thinking about my similar triangles, what I'm going to do is I'm going to use the ratio of the vertical distance and the ratio of the horizontal distance. So in the small red triangle, can you see that that ratio, and I'll write it in red, if I do the height divided by the length, I would have 2 over x. And on the big purple triangle, now my height is y, and my whole length is 10. And so the ratio of 2 over x is going to equal y over 10. And at this moment, we can, you've got some choices here. You could do the derivative right away on this. And on the red side, you'd have to decide what are you going to do with that x on the bottom. Are you going to use a quotient rule? Are you going to bring it up to the top and make it x to the minus 1 and use the chain rule? Those are all options. You could multiply this out. Here, I'll do it in 2 ways. Okay? Option 1. You decide that you would like to do, I'm going to change that to 1/10. And you take the derivative with respect to time of this equation. We'd have a chain rule here. The -1 would come out in front. Subtract 1 from the exponent. Oops. Times dx dt. Derivative here would be 1/10. dy dt. And then you could plug in what you know. The x squared would go to the bottom. We're finding that when x is 7, so x squared would be 49 times 1.2. And multiply over our units. Multiply both sides by 10 and simplify it. You'll get -24 over 49 meters per second. The other option the other option is you could have multiplied this out like that. And then you would have a product rule when you did the derivative. So when I take the derivative with respect to time here, derivative of 20 will be 0. Keep 1 the same, derivative of the second one, plus keep the second one the same, derivative of the first one. And notice the difference. In the second one, we need to know y. In the first one, we didn't have to know what the value of y is. We just had to put in the value of x. So if we're plugging in things that we know that x was 7. dy dt is what we're trying to solve for. And dx dt is 1.2. We still need to figure out what y is. And the way that we figure out y is we would have to go to our ratio here and say, if I know that, oh, I lied. I made some mistakes. Okay. No, everything is still, yeah, 3 meters away. I'm okay. I got, with the x's switching around, I got my 3 and my 7 mixed up there. We're still all good. X is 7. So we would set up that 2 over 7 is y over 10. So we would figure out that our y value is 20 over 7. Which when we multiply this out, this is negative 24 over 7. If I move that over, I would get negative 24 over 7 equals 7 dy dt. Divide both sides by 7, and we do get exactly the same answer. And now we're going to do, I think that, do I have another? No. We're going to do another one, another similar triangle question. That I stole from your textbook. And this one kind of bothered me, you know, many times because it felt like there wasn't very much information given. And when less information is given, it feels like this is harder. So water skier skis over a ramp shown in the figure, and they're traveling at a speed of 12 meters per second. How fast is she rising as she leaves the ramp? So what we have a ramp where the speed is being constant at 12 meters per second. And as a result of going up, the y value is changing this way, as well as the x value changing that way. What do we know? We know that, I'll use z, dz dt is 12 meters per second. We want to find dy dt equals what and when at y equals 1. So here's the start of our setup, okay? But when I look at this, this is a right-angled triangle question. But it has y changing and it has x changing. And they want us to find dy dt, but it feels like we don't have enough information because we have no information about x. So when we look at this, our normal start to this equation would say, well, I would use x squared plus y squared equals z squared. And if I take the derivative with respect to time, I'm going to have an x value that I need, a dx dt, a y value, a dy dt, a z value, and a dz dt. And the problem right now is I don't have the dx dt, so it's going to be hard to solve for dy dt if I also don't know dx dt. So this question also requires that we use similar triangles. And the way that we use similar triangles is if we take this ramp and we imagine they are somewhere along there where this is x and this is y, but the ramp has an overall situation like this, we just created a similar triangle. That the x and the y, wherever they are along that ramp, is a similar triangle to the big one, which has the 1 and the 5. So if we use ratios, we could say that y over x is always 1 over 5. And what that allows us to do by rearranging this, so we can multiply both sides by x and multiply both sides by 5, is we can say there's a relationship between x and y. That x is always going to be 5y. So we used right-angled triangles to set up our equation, but we had to use similar triangles to get a relationship, and now I can substitute the 5y in for x, so I have an equation that just has y and z. What will this allow me to do? I can now take the derivative with respect to time of this equation. And we're trying to find this when the y value is 1, so the x value would be 5, and a squared plus b squared equals c squared would tell me that my z value is the square root of 26. So plugging everything in, 52 times 1 dy dt equals 2 times root 26, and we know that dz dt is 12. Yes. Multiplying this all out, will give us 24 root 26 over 12. Meters per second. So here was a question that we needed to use similar triangles and right-angled triangles to solve. We've used similar triangles in the volume questions when we had a cone. So it is a strategy that seems to come up a fair bit in related rate problems as a way to make a relationship between two variables so you can substitute a variable out of the equation. Okay? But whenever you have to substitute a variable out of the equation, that makes it a more difficult question. So as far as how do I go about trying to solve one of these if I'm doing it myself and I'm getting stuck? Okay? So we're doing our setup, we're setting up our equation, and at this moment when I set up the equation, I notice something's going to be wrong. I don't have enough information. okay? When you're getting into that situation where you have too many variables or you don't have enough information, you have to think, well, what way could I change a variable? And often similar triangles is going to be that strategy. All right, how many examples do you guys have left